All right, so here's our problem to focus on. It says prove that the fraction 21n plus 4 divided by 14n plus 3 is irreducible for every natural number n. Okay, so just as a quick reminder, the natural numbers basically start from 1, and they're the counting numbers that go all the way up to, but not including positive infinity. So we have to prove that a fraction is irreducible, but before we do that, it helps to talk about what irreducible actually means. So irreducible means cannot be reduced. So if I have a fraction like 1 over 2, that can't be reduced, whereas a fraction like 3 over 6 can be reduced. So the first step that I took when I approached this problem, to be frank, is I actually divided the 14n plus 3 into the 21n and the 4. And I broke up this fraction into a sum of fractions. And I thought that if I could prove that at least one of these terms was irreducible, or both, that the entire sum had to be irreducible. And I made an argument, but the thing is, this is false, because if I have a fraction like, say, 1/4 and 1/6, which are both clearly irreducible, they're clearly in simplest form, the sum of 1/4 and 1/6 is 10/24, which is reducible. Okay, so this argument was actually not valid, but that was kind of the first thing that I tried. The next thing that I tried was I thought about what it meant for a fraction to be in simplest form. So if I take a fraction like 9 over 6, which is clearly divisible by 3, what makes that different than, say, 2/7? Why are those different? So it turns out that there's a famous lemma called Bézout's lemma, which answers that very question. And hopefully maybe I can make a video discussing it, using some examples and proving Bézout's lemma, but it says the following. It says that if I have two numbers, a and b, there have to exist integers, which, by the way, integers represented by this z, if you see a z, and it means all the numbers, all the counting numbers from negative infinity, including 0, and going off to positive infinity. So it includes more possibilities, but there must exist integers x and y such that this combination, okay, of xa's and yb's, when combined, gets you the greatest common factor of a and b. Okay? So just as a quick example, suppose that I have 9 and 6. So in order to be reducible, that means there has to be some sort of common factor or greatest common factor between 9 and 6. If there is a common factor, there has to be a greatest common factor. That's just a simple result of set theory. But 3 is clearly the answer here, but let's see. If that's true, that means I should be able to find numbers x and y, integers, such that 9x plus 6y must equal the GCF. Well, the GCF of 9 and 6 we know to be 3. So we're basically trying to find x and y such that 9x plus 6y equals 3. So at this point, you might just want to pause the video and see if you can come up with values of x and y that make this 3. Okay, so if I'm just looking at this for the first time, clearly one of these has to be negative. If x is positive, 9 grows faster than 6. So I would argue that, one of these has to be negative. So the first thing that I would probably try is let x equal 1 and y equal maybe negative 1. Then we have 9 times a positive 1 plus 6 times a negative 1, which is 3. So since we found x and y, now there are multiple values that would make this work, by the way. Multiple values that would make this work. But the point is, if you can find at least one pair of integers that make this work, that means that the greatest common factor is indeed 3. Notice that it would not work if I said the greatest common factor was something like 4, because it is impossible to find integers x and y that make this work. You can kind of convince yourself of that. But okay, let's go back to our problem. Okay, so clearly we don't have numbers here. 21n plus 4 is not a single number. It is a set of all possible numbers where n could be anything. So it's going to be a little tricky, but what I like to do in these situations is I like to start small and ask myself, how would I answer the question if n were, say, 1? So let n equal 1. So now all I have to do is I have to prove that 21 times 1 plus 4 divided by 14 times 1 plus 3, I have to prove that that fraction is irreducible, 25/17. Well, clearly it is because 17 is a prime number, but if you keep trying numbers out, I think n equals 3 will get you a denominator that is not prime. So how can I show this? Well, to show this, I use Bézout's lemma to find x and y such that 25x plus 17y equals the GCF of 25 and 17. Well, if 25/17 is irreducible, what do you think the GCF is going to be? What's the greatest common factor of 25 and 17 if the fraction can't be reduced? Well, 1. 1 always goes into any pair of numbers. So I have to prove that there exist x and y such that 25x plus 17y equals 1. Okay, so let's see. If x equals 1, if x equals... Yeah, see, the problem with this is I don't know. And it might take hours or even days to find this. But this is only for n equals 1. So I have to be very intelligent about designing a system that will always give me x and y such that this works. And now it's time to bring in the Euclidean algorithm. So the Euclidean algorithm basically says, if I have that 25x plus 17y equals 1, I want to write 1 in an intelligent way that actually gives me some numbers of 25 and some amounts of 17 combined to get me 1. Okay, so how does one do that? Well, what you do is you take the numbers 25 and 17 and you actually divide them. So remember that 25 divided by 17, yeah, that might be irreducible, but when you divide it, you might have learned in elementary school that 17 goes into 25 a certain number of times. And you can actually write the result as some number of 17s plus a remainder, okay? So I can rewrite 25 as 17 times some number. Okay, in this case, it has to be 1 because 2 goes over my little limit. So 17 times 1 plus 8. Okay. Now that remainder of 8 is very important. And what the Euclidean algorithm tells me to do next is do the exact same thing with 17 and 8. So now I'm going to rewrite, maybe I'll do this in a different color. Now I'm going to rewrite 17. Now I'm going to rewrite 17 as a certain number of 8s plus a remainder. And as soon as this remainder is 1, then I'm done. Because that's what I wanted in the first place, right? And now by breaking it up like this, it turns out that I can substitute back in and go up as much as I need to in order to write 1 as a combination of 25s and 17s. So let's go ahead and do that. So I'm going to start here. And if 17 equals 8 times 2 minus 1, or plus 1, that means that if I subtract 1 from both sides, okay, I get that, or I'm sorry, if I subtract 8 times 2 from both sides, I get that 1 is equal to 17 minus 2 times 8. Okay, but then I can actually solve for 8. Because 8 was already written as a linear combination of 17 and 25. More specifically, 8 can be written as 25 minus 117. And then I'm done because I rewrote 1 as a combination of 17 and 25. How many 17s and how many 25s? Well, by distributing this, all I have to do is distribute this to get that 1 equals 17 minus 25 times 2. Two negatives make a positive. This is going to be positive 2 17s. And then if I have 1 17 plus 2 17s, this gets me this. Which, if you compare it to what I had up here, I have that the GCF of 25 and 17 can be written as a linear this is called a linear combination of 25 and 17. So in this case, my x is -2, and my y is +3. Something that I probably wouldn't have come up with myself, if I'm being perfectly honest. Okay? So it stands to reason that if this linear combination works with n equals 1, it turns out that this linear combination will actually work for the general case, but we still have to convince ourselves of that. And the way to do it is to repeat this for the polynomials 21n plus 4 and 14n plus 3. So this is how you do it for numbers, which is actually really cool in and of itself and can be its own separate video at this point. But how do we do it for numbers? Okay, so I'm going to go back up here to remind ourselves of 21n plus 4 and 14n plus 3. Well, we're going to do the same thing. So in order to prove that that fraction is irreducible, it stands to show, so we need to show that there exist integers, and I say integers because these can be negative, integers x and y, such that the linear combination of the numerator and the denominator is 1, which is the greatest common factor between these. If it's irreducible, it has to be 1. And we're going to do this in exactly the same way. We're going to use the division algorithm. So this is written very specifically to show you that clearly this is bigger than this. All right, it starts out at 21, and then we're adding 4. So there's no chance that 17n plus 3 will ever surpass 21n plus 4. And since the first term is bigger than the second term, what we can do is use polynomial division to divide 17n plus 3 into 21n plus 4. Well, 17n is going to go into 21n one time. And when I multiply this out, I get 17n plus 3. I take 1 times the whole thing. If I subtract everything now, I get 21n minus 17n is 4n. 4 minus 3 is 1. All right? So just like before, I can write, do this in a different color. I can write 21n plus 4 as a combination of 1 17n plus 3 plus 1 4n plus 1. And I play the exact same game again. I see that 17n plus 3 is clearly bigger than 4n plus 1, and I see how many 4n plus 1s can fit into 17n plus 3. So repeating the polynomial division here, how many 4n plus 1s will fit into 17n plus 3? Okay. If this is a 4, then 4 times this quantity will get me a 16n plus 4. a 16n plus 4. And then when I subtract, wait, I think I copied the problem down wrong. Oh shoot, because I was going to say, this should be a 14n plus 3. All right, I'm so sorry about that. So 14n plus 3. All right, that doesn't change too much, except when we divide it into this term the first time, we'll get a 7n plus 1, which means this will be a 14n plus 3 and this will be a 7n plus 1. Okay, now when I divide it in, I should get something nice. So if I look at how many 7n plus 1s fit into 14n plus 3, if I guess 2, then 2 times this will get me 14n plus 2. Subtracting will give me just a 1, which is perfect because that's exactly what I wanted. So now I used this and this for the second part of my Euclidean algorithm. So then I can rewrite 14n plus 3 as 2 7n plus 1s plus 1. And that one term, just like above, when we got one, let's see, down here, we were done, because then we just solved for the 1 and rewrote 1 as a linear combination of the numerator and denominator. So let's go and do that to finish this off. One is going to equal 14n plus 3 minus 2 of the 7n plus 1s. Okay, but the 7n plus 1 can be rewritten as the 21n plus 4 minus 14n plus 3. Okay, so I get that 1 equals 3 14n plus 3s. Okay, 3 14n plus 3s minus 2 21n plus 4. So basically, this is the numerator and this is the denominator. That was the numerator, this was the denominator. We have found x and y such that this works. Because I think the x goes with the 21n plus 4, which means that here x equals -2, which means that y equals a positive 3. Notice that we got the same exact thing as we did all the way above. We still got -2 and 3, but this was not sufficient. Now, if the proof asked you to prove that this expression is irreducible, plugging it in for n equals 1 and doing that, you might have actually been able to just skip all of this, skip the polynomial long division entirely and just guess this. I mean, it has to hold for all n's, so it has to hold for n equals 1. You could have gone straight to the solution, and as long as -2 of the numerator and +3 of the denominator combine to get you 1, then I claim you're done and you've proven that this fraction is indeed irreducible. And that's a good place to stop.